So you should be starting to develop a bit of an understanding about how generalized linear models work and how they allow you to accommodate data that are not necessarily going to conform to the assumptions of a Gaussian linear model. We've discussed measurement data with our log normal generalized linear models. But now let's move on and talk about count data. Count data, which is to say just integers, counts of things, are similar to log normal data or measurement data in that they are bounded by 0. You cannot have a negative measurement, just like you cannot have a negative count of something. The difference is that count data are discrete, while measurement data tend to be continuous, at least theoretically. And so when you're counting things, right, you can't really have a value of 23.4 like you could with a measurement of 23.4 centimeters. You either have 23 of something or you have 24 of something. And this has a lot of implications for kind of probability distributions and the types of generalized linear models that we can use for count data. And so to explore some count data, let's load in that Goldman data set that we used before. Set your working directory and pull in that CSV, read that into R. Now, what I want to do, let's click on the Goldman data, or you can use the view function. We want to explore count data. And so what we're going to do is look at columns 8 through 16 here. If you scroll over and look at those, these columns are labeled L-hum, R-hum, left humerus, right humerus is what those stand for, L-rad, R-rad, left radius, right radius. And these columns take values of 0 or 1. They are basically presence or absence data of whether or not this element was present for that individual skeleton in the row, because each row is one skeleton, one individual. And so if the way that this database was coded, 0 values mean that the element was present, and 1 values mean that the element was absent. This is a bit kind of the opposite of what you might normally expect, but that's how it was coded, so we can work with that. I figured that out from reading the metadata PDF that's associated with the Goldman dataset. I've got the link to that in the PDF associated with this tutorial as well. And so what we need to do, really, is for each individual, right, I want to add up the number of missing elements in these rows, or in these columns 8 through 16, right? So I want to add columns 8 through 16 for each row in the data frame so that we know the number of missing elements. Because fortunately for us, the way that they're coded, 1 being a missing element, if we just add up the number 1, or the kind of all the instances of those number 1s, we'll get the total number of missing elements. And so the way that we're going to do that in R is I want to create a new column in the Goldman data frame, and I want to call it missing in reference to missing skeletal elements. And what we then want to do is basically take the sum of columns 8 through 16 for each row. If you were to do this in Excel or something, that could take you a really long time to do manually. In R, we can do it with one line of code. We're going to use the apply function. And the way we do this with the apply function is to say, all right, we're going to apply the sum function, which is a function in base R that just calculates the sum. It adds things together. We're going to apply the sum function to each row in our data frame. And the data frame that we're feeding this apply function is the Goldman data frame, but we're indexing it for all rows, because it's a space and then a comma, and we want only the columns 8 through 16, because I looked at the data, and columns 8 through 16 are denoting the presence or absence of these measurable elements. And so by saying Goldman brackets 8 through 16, it restricts us to just those couple of columns, and that's what we want to then take the sum of. You can see those right here in the R console if you run just that part. And so the apply function is applying the sum function to each row of that data frame. The 1 that I've got highlighted here in the middle of the function, that denotes rows. 2 denotes columns. You can find that in the help page for the apply function. So we're applying the sum not to the columns, not adding up the total number of missing humeri across all individuals, but adding up the total number of all missing elements for each individual. That's why we're applying it to the rows. And so if I run this, we now get a new column added to the end of the Goldman data frame that contains, for each individual, for each row, the number of missing elements, because I just added up the numbers, the number of instances of the 1 in those different columns. So now we've got that. And now if we think about what we're dealing with here with these count data, these counts of missing elements, we can start to understand why a linear model wouldn't be appropriate in this context. Right? If you recall, the assumptions of a linear model are that, first, that it makes kind of real-world biological sense, right? And that, obviously, we're going to run into problems with if we try to model count data, because count data are bounded by 0. And as we saw in the previous tutorial for a log-normal generalized linear model, when we try to plot measurement data that are bounded by 0 using a regular LM function, that model fit just runs from positive infinity to negative infinity. It does not stop at 0. And so we need to do something different to accommodate that. Use a GLM with a certain type of link function, as we talked about previously. So that's kind of the first reason why count data, just like measurement data, are not going to work that well for a linear model. The linear model is going to predict values that don't really make real-world sense if we let it be Gaussian, as the default is. Additionally, when we're thinking about the residuals of the model, assumptions 4, 5, and 6, we need those residuals to be independent. That's a given for any type of model. But a regular linear model, a Gaussian linear model, requires additionally that those residuals are homoscedastic, that they have homoscedasticity. I mean, that the variance is kind of even in the residuals across the model fit values. And also that those residuals are normally distributed. Now, count data, right, because they are discrete values, because they're integers with no decimal places in between, right, they actually can't really be normally distributed around your model fit. Right? With measurement data, like we were dealing with before, it was possible for those to be because they're continuous. And when you fit a model to it, you end up with residuals above and below the line. So you have positive and negative residuals. So that fits normality, right? Positive and negative. And the fact that it's continuous because their measurements allowed that to happen. But if you were to fit a model fit to count data, you would have positive and negative integers, yes, but they would still be integers. They wouldn't be continuous data, so they couldn't really be normally distributed. And so you'd be violating the 6th assumption of a linear model that we're talking about here. Additionally, assumption 5 of the data being homoscedastic. Count data are actually not hardly ever homoscedastic. Heteroscedasticity is known to characterize count data, and we're not going to get into the reasons why, but that's why you can't really use a Gaussian distribution that well for these types of data, because they're pretty much by default going to violate those assumptions. And so we know that we're violating at least 3 of the assumptions of a Gaussian linear model just by definition of using count data. And this is why we need to move on and use a generalized linear model. In this case, a Poisson family generalized linear model. But before we get into modeling these data, we need to continue to clean them up a little bit. So we've got our missing element column added. Now I want to subset the whole data frame. I want to create a new object called GoldSub, and it's a subset of the Goldman data. And the reason for this is we've got our count data that we want to be the response variable, but I want to know if different locations have differences in missing element numbers. So I want to subset this by location. And the first location, I picked 3 locations that had the highest sample sizes. I'll start off with the United States as our first location, Alaska specifically. The second location is going to be also the United States, but Utah, United States. And then the third location we're going to look at is Japan. And so what we're doing here with this subset function is we're saying subset the Goldman data frame that we loaded in above and added a new column to. And I want to subset it according to the location column, which is a column in the Goldman data frame. I want the locations of Alaska, or, which is denoted by the vertical bar, locations of Utah, or locations of Japan. I want those, any row that has those three location values in it, keep those, and make them a new data frame called gold.sub. So now that we've got gold.sub, I actually want to also kind of make that location column a little bit easier to read, right? Because if we look at gold.sub, gold.sub $location, I just want the location values. Alaska, comma, United States, Ohio, comma, United States. Those are big character strings, right? It's a lot of words. So we can do a little bit better than that, right? I want to recode those using the recode function. Now this function is in the dplyr library, so let's load that library. If you haven't already installed it, you need to install it, but you should have it installed. Load up the dplyr library, and now you have access to the recode function. And what I want to do is recode gold sub location, and I want anything where it says Alaska, comma, United States. Let's move this down to a new line. Alaska, comma, United States, I just want that to be AK, right, the abbreviation for Alaska. Then I want any instance of Ohio, comma, United States to just become OH, right? We're just going to make this easier to work with, so I don't need to type out Alaska, comma, United States every time I want to pull up the Alaskan data. And finally, let's call Japan JP. So we run this function, and now we've got, instead of those big, long character strings of location, we've got just the two-letter abbreviations for each case. Although it looks like I messed up because I for one of them I put Utah for some reason, and now I put Ohio. Let's do Ohio. All right, let's go back, subset, create gold sub. Now let's do that. Here we go. I've got to keep my things consistent. I'm not sure why I thought Utah. But yeah, now we've got just two-letter abbreviations for each of them. And that's a lot easier to work with. Now you'll see that these two-letter abbreviations are in quotes, right, which is what we'd specified. And that means that they are character data. R is understanding that they're characters. Let's inspect the structure of them real quick. So we can see that it says CHR here. These are characters. So it knows that these are words. But what we want to do is actually convert these to factors. Now a factor is, as you'll recall, what R refers to kind of categories as. So right now, because this is a character string, or a character vector, location is a character vector, R understands that AK is a word, that OH is a word, that JP is a word. But what it doesn't understand is that all of the instances of AK are actually all belonging to the same category, AK. It just thinks these are words. It doesn't understand that the same word within the same column is all related to each other. And so to do this, to make sure that R actually understands that we're dealing with categories, I want to use this as factor function. If I do this, if I wrap gold sub location in as factor, it converts these to factors. Now if I just ran that, I overwrote gold sub location and made it a factor. Now if I inspect the structure again, we can see that it no longer says CHR in the structure, it says factor in the structure. So now it knows that these are groups. It knows that these are three different groups, that AK is not just a word, but it's a word that's referring to a bunch of the same kind of grouping. So now we understand a bit about kind of count data, what we're going to be dealing with, and we've got our data all in order for us to next start fitting a generalized linear model.